Hello, this lecture is on network synchronization. I'm going to describe how we populate the nodes of a network with phase oscillators, and then we will look at the phenomenon of synchronization, first with just two phase oscillators that synchronize. And then what we'll do is look at a complete graph where every node is interacting with every other node, and that'll demonstrate a Kuramoto phase transition. So the synchronization of phase oscillators is one of the simplest sort of collective motions that you can derive. And so what we think of as an isolated phase oscillator, this would be the dynamics of this node. And so this is a network with just two nodes and a single link. And so this oscillator is oscillating with an angular frequency of omega 1, and this is oscillating with an angular frequency of omega 2. So they're just free running oscillators. Now the dynamics that we want to impose on this is where we look at the time rate of change of the angle, and then in the absence of any coupling, so this G is a coupling that occurs along this link. Without any coupling, we just have the original free-running oscillators. But when we turn the coupling on, when we make G1 and G2 non-zero, and we're coupling them with this function, now this is a nonlinear function, it's just a simple sine, but it's obviously not just a linear difference between theta 1 and theta 2. This nonlinearity with the coupling will actually allow this system to show very interesting dynamics. It's going to show frequency entrainment, and it's also going to show locking and synchronization. Now we start with what looks like a two-dimensional flow, but in fact what we can do, there's a sort of a trick. It's called slow phase, and so what we do is we just subtract one equation from the other, and we define this new phase angle phi, and so phi dot is just the difference of the theta dots. And so that's the difference of the frequencies, and then we've got this coupling term which now has combined into a single coefficient in front of the sine of that slow phase. So this is now a one-dimensional dynamics, and so one-dimensional dynamics are very easy to analyze, and so we can figure out when there are going to be nodes or fixed points in the dynamics, and when there won't be. And so in this case, it's really easy to see that we just have to plot phi dot as a function of sine phi, and this is an offset. So what we're doing is we're considering a case where if the frequency difference is 0, and that's when omega 1 would be equal to omega 2, then all we've got is this simple sine, and then it has an amplitude of g1 plus g2. And so you can see that this sine, this red curve, and this is the average difference in the frequencies here. So this is the frequency offset of the original oscillators. But when the amplitude of this sine wave intersects the line at 0, then we're going to have these fixed points. That's when phi dot equals 0. And if you just look at the slope, this is the attractor, so that's going to be our synchronization point. And there's also a second fixed point, but this is unstable. That's actually going to be a repeller. And so what we have is that in order to have a fixed point, which means synchronization, then the frequency offset has to be less than the sum of G1 plus G2. So this is a synchronization condition that we have derived on these very simple dynamics. And we can also solve when phi dot equals 0, there's going to be a fixed phase, sine phi star, so that's the fixed point phase. And there's also going to be a compromise frequency, omega star, and that's just a weighted sum, weighted by the G factors of the two initial frequencies. So this is what the frequency entrainment looks like. And so the locking, or the fixed points, occur when the total G, so this is G1 plus G2, so this is just redefined or rescaled G. But when the coupling is greater than the frequency offset, then there is a fixed point and these will lock. But what's interesting is that even if G is below the critical G, so the critical G over delta omega equals 1, when you're below the critical G, you still actually have what's called mode pulling or frequency entrainment. So you see that these two frequencies, so we're starting with one oscillator has a frequency of 0.1, and the other one has an oscillator, or the other oscillator has a frequency of minus 0.1. And so as G increases from 0, these actually pull together to the compromise frequency. Now in this case, the compromise frequency was just set to be 0 between these two. All right, so now what we want to do is we want to populate the network architectures with these phase oscillators. So I looked at a very simple network that had 2 oscillators. Now let's look at networks that have maybe 128 or 256 nodes, and we populate those with phase oscillators, and they have random phases over some distribution that has a width delta omega. And so these are all going to initially be free-running oscillators with different frequencies for each node. These are 2 different architectures we could look at. I'm actually not going to do these in this lecture today, but you could look at an ER network, which is the random network, or a small world network, which is an example down here. Here's the distance matrix for the small world. Shows a lot of structure for the random. Actually, not essentially no structure on that. And so what we're going to do is we're going to populate the nodes with these free-running oscillators, and then we're going to couple them, but now we've got n simultaneous differential equations. So if n's large, if n's in 128, 256, or in the hundreds, that is a difficult problem to solve. And so what we want to do is either numerical simulations, which is this example, and so this happens to be a 16 by 16 square lattice, and as g increases, you'll notice that a lot of frequencies will entrain. So if there are nearby frequencies that are nearby on the network, they'll entrain into a single compromised frequency, and then that'll entrain other frequencies, which entrain other frequencies, and these all kind of cascade down into a frequency synchronization when the entire network is synchronized. In this case, the delta omega was roughly 0.2, and you can see that when g is greater than about 0.2, it's not as sharp of a transition. It's a little bit more gradual for the square lattice, but you can see that when you're at a range of a g of 0.2, that it'll synchronize. Now that's the numerical solution, just putting it into an ODE solver. But we can also approach this analytically, and the way we do that is through something known as mean field theory. Now, mean field theory is a way of looking at how a n-body system has average properties, but then the individual elements of that system will be interacting with the average properties. And so you actually get a self-consistency equation that you can solve, and you can solve that for the critical strength of the coupling to have a transition, a synchronization transition. So in this case, we've got these phase oscillators, and so we could either view that as real valued angles, or it turns out that it's very convenient to think in terms of complex phase angles. And so these are actually phasors, right? We can think in terms of phasors. So each phase oscillator is actually contributing a little complex part to a total sum. And so we're summing from oscillator 1 to n. They each have their individual phases. And so these are all little phasors of unit length. We divide by n to normalize. But what this produces on the complex plane, when you think of this as a sum over these random phase angles, it's actually a random walk. And random walks on the two-dimensional plane have very well understood properties. For instance, the average size of the mean field is actually 0, but its variance scales as 1 over n, right? So this is sort of classic, if you take the square root of that, that's the classic 1 over the square root of n behavior on a standard deviation. And so this is going to allow us to actually construct a mean field amplitude and also a mean field phase. And so here, let's look at a Kuramoto phase transition. So this is when we have a complete graph. Every node is interacting with every other node. And we populate those with these phase oscillators, and we couple them. And this is the adjacency matrix, but in this case, it's all ones, right? Because every node is connected with every other node. So what we have to do in this case, rather than put this into an ODE solver, which we could do, but we want to work analytically. So we define a mean field. So here's the mean field amplitude, and here's the mean field phase, and it's just this sum over these individual unit phasors. And so the overall, the mean phase angle will be equal to omega bar, that's the compromise frequency, times time. And there's also going to be a slow phase, and the slow phase will be the individual phases of the oscillators relative to this mean phase, which is increasing linearly with time. And so when we do that, this sum over n objects actually turns into a single equation, which is just one-dimensional dynamics again. And so we've got one-dimensional dynamics just as if we were coupling two simple phase oscillators. And we can solve for the critical coupling coefficient that's going to give us complete synchronization. And so taking a look at how we would work with slow phase, and so here now is the phase difference, and so we've got the individual frequencies of the oscillators relative to the mean frequency, and then we've got the coupling term, which is going as the individual slow phase of the oscillator. So we can solve this for when d psi k dt equals 0, and that gives us this equation here, which we can then solve for the phase of the kth oscillator. And so that's going as the arc sine of this frequency offset divided by gk. Now, what we want to do is work with a distribution of frequencies. So rather than just assuming that there's some delta omega of frequencies that we're populating these oscillators with, let's go ahead and actually use a probability distribution. For instance, we can have a probability that varies as a function of omega, and it can have a mean frequency, but it'll have some distribution around that. And this could be a Gaussian, but we'll see actually that it works very easily if it's a Lorentzian, and so we're going to actually assume that this is going to be a Lorentzian. But we still have to find a self-consistency condition. And so first of all, what we've got to do is figure out what fraction of the nodes are synchronized. And so that's this n sub s. And so what number or what fraction of these is going to be synchronized? And so we can actually expand this differential. So n synchronized of psi d psi. That's going to be this distribution of frequencies. And then we convert the d psi into a d omega d psi, take the absolute value of that, and then that's going to be varying as d psi. This d omega d psi, the reason we do that I could put a little k there, because this is now going to be the derivative of the angular frequency of the kth oscillator relative to psi sub k. And just from the previous equation here, we see that this is going as sine psi k, and so then this will, after we do the derivative, will be cosine of psi k. And so then this gives us an expression for n of s. This is the fraction of nodes that are synchronized. Again, going like this, but now we plug it in. And so this is gk coming from here. Here's the cosine, which is coming from here. And then this is the probability distribution function, but it's now a function of this argument, which is the mean frequency plus the coupling term. So the mean field now, rather than a sum, is going to be an integral from minus pi to pi, and we're going to integrate over the slow phase relative to the mean frequency. And what we're really doing is just finding the average number of synchronized nodes, because these contribute to a mean field. If they're not synchronized, then the average phases average to 0, right? And so the only way that we're going to get a finite or a non-zero mean field is through those nodes that are synchronized, because they're going to be adding coherently to this mean field. And so then in this case, what we'll do is just plug in for n sub s, which now is going to go as cosine squared of psi, and then we've got our probability distribution function, and we're just going to be integrating that over all the phase angles, in this case from minus pi over 2 to pi over 2. All right, so now what we're going to do, I mentioned, it could be a Gaussian, and it's kind of a natural choice. But an easier analytic choice is a Lorentzian. And so this is a classic Lorentzian. So this is going as a frequency difference squared plus a line width. And so gamma is typically viewed as a spectral line width. For normalization, there's also another factor of gamma up here and also a pi that shows up there. But this is a probability distribution function that actually integrates to unity when you integrate this over omega. So we plug that in to this equation, which we saw before. And so now we've got the cosine squared going over this Lorentzian denominator. And you'll notice that we've got a k e to the I omega bar t. So this is the mean field, but we've also got the mean field over here. And this is the self-consistency equation. This is where the mean field is a function of the mean field. These cancel out, and what we get is 1 equal to this expression over here. So what we have is g, or what we're looking for is g as a function of k. This is an easy integral to look up. The g sub c turns out to be equal to twice the bandwidth, or the full bandwidth, and the mean field then has this classic square root dependence, where it's just g minus the critical coupling. And so then this is what we get when we put it back into an ODE solver. So this is looking at it numerically. The analytic solution is up here. G sub c is equal to 2 gamma. And then the mean field has this classic square root behavior that all mean field theories tend to have. Now this is actually a slower function than what we get in the simulation. So the square root actually comes up a little bit more slowly. It's still abrupt, comes up with infinite slope, but it's a little bit more smooth. The actual Kuramoto phase transition is very abrupt. And this is for 256 oscillators. If we actually increase that to 1024, this would almost be like a step function, in which case the mean field approach is not highly accurate. It captures the phenomenological behavior of the transition, but the mean field will tend to be a softer transition than what this system actually shows, which is this very abrupt transition. All right, and so in summary, we've looked at synchronization on networks. We began with just 2 oscillators that were synchronized, but we ended with the Kuramoto phase transition. And this is a very important analytic result because it shows a number of important properties that connect up with broader areas and other parts of physics. For instance, it's a mechanical analog of a thermodynamic phase transition, what's actually known as a second-order phase transition. Second-order phase transitions have an order parameter that tends to come up discontinuously. And for instance, when you're looking at superconductivity, you'll actually look at the superconducting fraction of electrons. And so this becomes what's called an order parameter. It's the fraction of electrons that are superconducting. In this case, it was the fraction of nodes that were synchronized. And so second-order phase transitions have this order parameter. What we did here today with the Kuramoto phase transition is it's purely mechanical. There was no thermodynamics at all, and yet there's a strong mathematical analogy to a thermodynamic phase transition. Another important point, we used mean field theory, and while mean field theory isn't tremendously accurate, it does capture the correct phenomenological behavior of this sudden collective phase transition, and that's the other point, is that this is a collective behavior of an n-body system. So we can analytically, using this idea of the mean field, calculate the behavior of a many-body system. And many-body physics is then a whole whole topic of physics. Very difficult to solve n-body problems, and this is one example of an easy problem to solve, an easy n-body problem to solve. And then also this connection to thermodynamics and also to stat mech.